Starting with the second session of the day. The theme of this session is smart water. Kicking things off, we have Dr. Vijaysai Prasad delivering the keynote address. Dr. Vijaysai Prasad is a part of the CTO office and heads the Water Technology Center, which is the hub of R&D, digital technology and knowledge management for L&T water and effluent treatment business. A chemical engineer by training, Dr. Prasad completed his PhD in system identification and controls from IIT Bombay. He has over 25 global patents, with many granted by US Patent and Trademark Office as the lead inventor. Water, hydrocarbon processing, and advanced analytics are his key areas of interest. He is now heading the Digital Twin Initiative for 120 MLD STP facility for L&T. I invite Dr. Prasad to the stage to deliver the keynote address titled Tangible Shift in Entitlement with Smart Water Solutions.
Yeah, very good afternoon, everyone. It's a pleasure to be here, and thanks for the organizing committee and Professor Sridhar for inviting me for this talk. And this is a nice opportunity to share some of the thoughts related to the smart water solutions. In fact, when I was thinking about what to talk today, I thought to strictly refrain from talking about how to solve a problem, because that everyone knows here very well and much better, but rather focus on what problems to solve, and which is more relevant to the industry. And as an industry person, I can bring forward those problems which require attention both from academic world as well as the industrial world here. So from that perspective, I just wanted to, in fact, talk about the current regulations, the guidelines, the bylaws, what we have in terms of right to water, what we got to now be focusing on, and what is smart water solution in that perspective, and how do we need to look at smart water solution, and where is the the role for AI ML and the other approaches to better the smart water thing, and finally we will conclude the topic. Before getting into that, I just wanted to place it in the context of where L&T comes into providing this smart water solutions. So what is the way that L&T water is structured is basically, I just wanted to take a time here. Yeah, so basically we have three verticals as far as the water division is concerned. WW, which stands for water and wastewater. Then III, which is irrigation, industrial and infrastructure, and water international. So when it comes to WW, basically we focus on rural water supply, which is the key initiative after this Har Ghar Jal mission now. So creating a tube well, creating the piping infrastructure, getting the taps at every house in the locality, and providing the water to every house is the part of rural water supply initiative. Of course, the urban water and water management is a slightly evolved version now. So the infrastructure is in place, but the whole challenge here is to how to reduce the non-revenue water now and improve the distribution and resiliency of the system. So that's the urban water management. And wastewater is a fast evolving business, and then we have already constructed about 2100 MLD capacity across the country for the wastewater treatment system. Coming to the irrigation, industrial and infrastructure, which is III, large water systems, of course, focuses on the farming sector, where we got to have the canals and the distribution channels to take the water. Of course, now it is involving and actually using quite a lot of smarter technologies to design piping network, taking it through the tougher terrains, valleys and stuff like that, and then laying the pipes so that the particular area is irrigated. So with the use of LiDAR and other technologies to achieve this has been quite prevalent now. And industrial and desalination, as the name itself indicates, it's more about treating the industrial effluents, make it reusable, and honor the 3 R's: the reduce, reuse, and recycle part of the whole story. Desalination is about treating the seawater and converting it into potable water, reusable water. So that's the whole solution there. Now the key focus today is about all the smart water infra. I will come to that very soon. Of course, the commonalities between what we have in the IIII is shared with Industrial International. So some of those capabilities are embedded into the Water International, and then we have those businesses running and in the international area. So overall we have 90 customers, I could say, as a water business, because we cater to mostly the government projects. So in India we have executed around 83 big projects, Middle East 5, and East Africa 2. So coming to the smart water infrastructure, which I basically wanted to cover more in detail, and the capability which I wanted to highlight more in detail, works on the industrial corridor creations, and it also looks at the town planning and the commercial installations, and then finally developing the smart cities is also part of the smart water infrastructure business. So we have Udaipur, Ranchi, Rajkot, Faridabad, Gwalior. These are the places where L&T has already been playing its role, and there is quite a lot of activities that are going on in terms of converting the existing cities into the smart cities there. So a quick track record here I would want to put in. So L&T Water has touched about 95 million people now. It has benefited them. 1 million hectare has been irrigated roughly in the country. So when it comes to water treatment plants and creating infrastructure for drinking water, around 7,200 KLD capacity has been created. Likewise, I mentioned about sewage water treatment, STP, so sewage treatment plant. So around 2,100 MLD capacity has been already built there. So smart infrastructure touches around 7,500 hectares, and of course around 5 lakh kilometer of water network has been created already by the L&T water team. So with that being the case, and referring to the smart water infrastructure that the business has, I just wanted to move to the next topic about what we call as a right to water, because this is all as the citizens what we need to be aware. And how the regulations and the laws that have come out, both in the international community as well as in India, to talk about this right to water and what it means to every citizen of the country. Now, when we look at the UN General Assembly in 2010, they talked about capacity building in the developing nations, particularly with the help of international organizations, basically to create accessible, affordable, and safe and clean water for all the users there. So subsequently, when we look into the Article 21, in fact, what India, it refers to India. So it also talks about the right to clean environment and right to health, but then it further clarifies that, the basic, right to health, when we talk about, it also embeds the basic clean water as a requirement to be fulfilled. So it's the right of every citizen here to think and, to use the clean water. And where it becomes the requirement on part of the government to fulfill that. Of course, in July 2012, there was also national water policy which talked about the stress that the water bodies in India is essentially feeling, and how that has to be addressed. And when we come to 2019, Har Ghar Jal Mission became the mandate here of the government, where every house has to be provided with a tap to fulfill the need of the nation. So when we talk about in this context, the drinking water and the policies associated with that, it is defined by the 4S today. One is the safe, and which is basically about the quality of the water, and subsidized, which is about the affordability of the water, and then sustainable, which is about the reliability in which the water is sent to every person, and sufficient water requirement, which is mostly about the quantity of the water that every person is supposed to be getting. So these 4 S are important in context of human rights and the right to water. And we got to, in fact, look into the policies and the further evolution of the topic in this under the 4S ambit here. So just a snapshot, this data is available very much in jalshakti.com in the government website. So how many houses have been completely connected with the taps today? So with the Goa, Telangana, and of course Haryana, they are all topping the list with 100% connections. Interestingly, some of the states down south, if you look into that, Karnataka is roughly around 59%. Of course, when we look into the Andhra, it is further lower. And Rajasthan, Jharkhand, there is a lot to catch up. So that is the way in which we got to look into the situation and then try to see how fast we can, in fact, move forward to bring the connection to every house and provide tap to every house here. Now, moving to the next topic, and which is basically driven by the 4S that I mentioned. And then the water distribution network, what we typically talk in this context. So it goes with a very typical network representation, what I have towards the left here. So basically this comes with a water source, and then the water source basically it puts it into the water treatment plant. From there we have the pumping station, and then energy reservoir or the elevated reservoir, what we have. Then from the reservoir, it's gravity to the different zones, zone 1, zone 2, and zone 3, whatever it is. So this is the basic infrastructure what we today have for the water distribution network. Now we got to look into the smart part here. So where do you bring the smart thing here? Because when we talk about digitalization, smart solutions, digital twin implementations, and then many other advanced operations related to this particular industry water, it's at a very nascent stage compared to the healthcare, transportation, oil and gas, and other businesses. Because there is an equation that has to be fulfilled. What is the investment, what you are going to do, and what is the return, what you are going to expect from here. So that equation is not quite favorable to, in fact, bring in the smart solution immediately into the water segment, because the kind of investment what you need to make on sensors to bring the required information into the system, the kind of investment what you need to do on data communication, they are all far more expensive compared to the returns what you get after having done all those solutions. I'm just want to give you an example here of a wastewater treatment plant. We made a small pilot study of a wastewater treatment plant, and then we invested some 10 lakhs or 15 lakhs to basically build that facility. Then we thought of, okay, let's automate it, bring all these SCADA, PLC, and others with minimum sensors to automate the whole plant. The investments went 2 times more there, just to bring the automation part to the treatment plant. And when you want to bring in the novel sensors and the new sensors that can bring in additional information on the wastewater treatment plant, the investments that were required went 3 times higher. So overall, you got to spend 5 times more than the actual cost of the plant in order to make this solution work. So is this really required? Or I can just manage with a good design and a very robust design, and then be done with it, and let the design take care of the treatability and the quality of the water that is getting discharged, rather than investing on the sensors and on the automation part, is something that needs to be thought. Or probably, how do we flip the problem? How do we come up with the smarter sensors or cheaper sensors that can give us the same amount of information what these expensive sensors would bring in? What is the way that we can basically work around in terms of automation to make the solution more meaningful? So that's the way we got to start thinking in the perspective of water here. So there will be definitely different views on this, and I would be very happy to, in fact, discuss about it. Coming to the integrated infrastructure project which L&T is working on smart cities, so it is more about the structured way of executing the project, and rather than bringing any smartness at this point of time. So as I told, we have a long way to go in the water domain to introduce that smartness. So a lot of things are on the paper, but then we got to understand that how to make them work in the real context. So when it comes to the structured implementation of the project in an integrated fashion, so what is the stormwater drain, the power duct, and the sewer network, and the potable water network, and the recycle water, so how they have to be placed in the proper context so that there is a minimum interruption of one running over the other, crossing the other, and then causing the disruption to the overall thing that happens beneath the ground, is what is the whole integrated infrastructure project concept is all about. So we earlier saw the simple water network design for a simple city, but then when we talk about a transition into a typical smart city, and then we want to bring in all the required smartness into the overall operation and the execution of the project, so then we basically have to think in a different way. Now, for this particular representation, what we have here, it starts with a reservoir to begin with, and finally the discharge system, what we have towards the end. But when you want to bring in the smart operations and the required intelligence into the overall thing, then what are the ways in which we can improve the overall the operation conditions of the city, is the energy efficiency part here. And then we have also been looking into the optimization of the overall network and the distribution challenges that are associated with that. The DMA analysis that goes into reducing the the non-revenue water here. And how do you schedule the pump operation so that the pressure and the conditions related to flow are taken care? And how do we fulfill the customer demand at every point of time without compromising on the required quantity of the water? And all these parameters do take precedence here in terms of converting one particular city into the smart city and bringing the required smartness into the overall operation here. Now I come into the ways that we can get into the specifics of each of those things. As I mentioned, there is a lot of confusion when we talk about smart water solutions and digitalization, automation, and the industry 4.0 or the water 4.0. Definitely, nowadays, any water distribution network has a SCADA, has a PLC or a RTU, and all these are provided in the central control room, and then people are continuously monitoring some of these parameters, but then certainly that is not what we need to be calling as a smart operation. That is the basic minimum requirement in terms of the automation what we need to have for any particular network. But then that allows the operator to visualize certain parameters, to basically operate certain pumps, flows, and things like that, and manipulate certain pressures, and then take the required control action depending on the information that is flowing in and he is able to see. So the next level above this operator is the timer-based controls, where certain scheduling of operations is there. So the certain valves open at certain specific times, and then certain pumps get triggered at certain time, and then there is some level of next level of automation comes in. The third is the fully automated one, which operators mostly don't like it, but then they have the situation where the algorithm takes care of the complete automation of the plant and the complete distribution and the requirement that is a particular network supposed to fulfill. The final one is the smart system here. So this is the highest in terms of the hierarchy, where it uses a certain historical data, certain information coming from the novel sensor, and it uses basically the analytics that is required to extract the information that is coming in, and how these analytics can be turned into useful insights that particular operators or the plant personals can basically use. So that is the next level of information. So this is just a representation of central command center for a smart city what we have, which in fact looks into the water networks, treatment plants, power network, and the smart street lighting, everything combined here. But then how do we basically bring in additional information that will help the operators and the plant personals to take more informed decisions and the right decisions. So that is the whole key here. So that requires basically the most important part in this is the data. So what data is being analyzed, what data is being modeled, and how this data is going to give that additional insight which the operator requires to take certain critical decisions. So it goes with a very famous statement by Peter Drucker. So he says that you cannot manage what you cannot measure. Very simple. So you got to have the relevant information to control something better, to improve something. You definitely need some relevant information that is coming in. But then there is also a very famous statement by George Fuchs from IBM: garbage in and garbage out. So if you don't bring in the relevant information which has the right source of knowledge embedded into that, and you keep on bringing something that is junk, what you get finally from the data is only the junk. You cannot get extra or useful information out of it. So we got to look into both the statements in this context and try to see how we need to deploy analytics to basically extract that relevant information, and that is useful in terms of operations and improving the performance of the particular system. So starts with a very fundamental descriptive, predictive, prescriptive analytics. Now it is going into the cognitive analytics, which is very important, and that is the evolution in a systematic way that has been happening. When we talk about analytics, from my experience, I can always say that what is the value of these analytics? The value is zero. There is no value with these analytics, but these analytics provide useful insights and the invaluable outputs that are required for the operator to make the right decision. So he is the one who is going to basically base his decision on what is the output that these analytics is telling him, what to do, what not to do, whether to do certain things or not. So that is what finally these things are supposed to be providing. Going into the next part of things. So what are those problems or the use cases that we can think in terms of improving the operation of the current smart city here? So very interestingly, there are a lot of possibilities that we can think of, but some of the things which we consider to be the low-hanging fruit is the better management of the overall water network here. So what we have is a reservoir, which is basically the supply source, and what we have is the consumer, who is basically the demand point here. So how do we basically balance between what is available versus what is being consumed by the consumer? So that is where a lot of interest is coming in. The systematic way of collecting the user habits here, which is a very important point here. So user habits is basically how a consumer is using water, what are the patterns that we typically get to see from the consumption what he is having, and what can be extracted out of it in terms of the demand that is creating at a specific point in a day, and how that demand profiles can be used to manage the overall network better, or an overall supply better, is the whole the key here and the game here. So it involves a lot of predictors here, because when we talk about creating that forecasting model about how the demand is going to grow, we need the right predictors. So as it is said here, it could be social, utility control, location, environmental, and also very specific to the houses and the buildings that are there in a particular locality. Let's talk about the social. So basically it involves about, it talks about what is the age group of the people that are living in the house, and what is the income source they have, what is the level of income that they are getting in, because a richer man can afford a garden in his house, and then he will start watering the garden, whereas the middle income group people, they may not want to in fact maintain a garden there. So definitely this creates a huge differences in the way the water is consumed per capita basis, right? And then you got to factor in those numbers. So some of those things get embedded into the predictors, and we got to basically choose the right parameters which will help you to forecast the things better there. Now when you talk about it involves a lot of experience. It's not going to be a black box model where you are going to just get the data whatever is available. It's not that. It has to go with a gray model approach, where a priori that something is going to be relevant. You try to focus on those variables and start getting and digging more information pertinent to those variables, methods, and then make them as a part of your model and get that useful information and the output out. So there are multiple techniques which have been used, and there is a literature that talks about the plethora of techniques which have been used here, starting from the regression model, the statistical methods, machine learning, artificial intelligence, deep learning. So these things have been beaten to death, and there is a lot of insightful information that has been derived out of it. And finally, we have been able to predict the demand profile very accurately with the time series models, and then link it with managing the whole supply better and manage our overall operation further better. So we have been able to then use this to control the water pressure more accurately, control leakages, schedule pumping operations, and the maintenance of the system, and infrastructure development. So all these things have been quite effectively achieved. But when you say we, I don't mean as a company, but in terms of the implementation that has been done in other parts of the world, what I actually was meaning here. These are all very relevant to the Western world there, where there has been very interesting studies that have been done. They have been proven, and they have been accurately able to predict the demand and the supply, and then build it into their water distribution network and get a better output. But we got to start initiating this kind of an approach. The second thing that is relevant to India particularly, because what is relevant to the Western world cannot be taken as it is and then applied to India, because we totally have a different situation on the ground. Our geography is different. Our utility pattern is different, our usage is different, our habits are totally different. So when given all these things, what is relevant for the country needs to be basically studied. Given the stress that we have in water network or the water availability is a very important factor here. So be it surface water or the groundwater or even the sea water extraction in terms of desalination, this is going to create a huge stress in terms of having availability for the fresh water there. So the key here is that how do we bring in analytics and machine learning and then the smarter solutions, basically to achieve the makeup minimization is the key here. So what is the way that we can minimize the makeup is by better using the wastewater that is getting generated. And earlier we used to just discharge it. Now that luxury is gone, and it will be gone further very soon in wherever it exists today. So better utilization of the wastewater to achieve certain utility applications. So for instance, it can be a fire hydrant, it can be used for washing vehicles, gardening, industrial applications. So these are the applications in which we will be starting to use the wastewater, and it has already been started, so that the fresh water that is required to maintain the overall water requirement comes down, and we have a better control over the makeup minimization here. So the complete water management is a more complicated topic here, because it is not about just makeup minimization in terms of the quantity. What is the quality of the water that we are essentially using in terms of the smarter solution here? We have various sources catering to the needs of the water. It can be a lake, it can be a borewell, it can be a river water, or it can be some desalinated water. So all of them are acting as the source for us to give the water. Now each of those sources come with a different quality and quantity, and then we got to basically understand that when this water is drawn into the city, what is the quality of the water that we are essentially using, and how do we basically keep a better control over the quality of the water. The problem gets more aggravated when we bring in wastewater into the system or into the whole equation. Let's think about the STP today in India. A very interesting fact here is that whatever the sludge that gets disposed from the STP, because we are talking about reusing the water into the circuit. So when we talk about the sludge that is getting discharged from the STP, it is said to be not suitable for composting. You cannot use it for agricultural purpose. The reason is what? Heavy metals. The sludge is having heavy metals, so where is the source of the heavy metals? The heavy metal is essentially coming from the water that is hitting the STP there. So Where did the heavy metals end up? In the water. So the water basically is coming from the sources from where it is being drawn. Is that measured? Why it is not measured? What are we drinking today? These are all the questions, but there is no answer yet, in the places where there is a spike in the heavy metal concentration. So those are the parameters which we need to start, in fact, looking into to manage the whole solution better and bring the smartness into the whole thing better. Finally, there is a tariff-based possibility that we can introduce here, because if we keep the tariff floatable, it helps us to manage the water network much better, which is not unfortunately the case today. And the analytics essentially can give us that leverage to manage the tariff better. So how? Because as you can see in the picture, when the cost of the water is high, the demand goes down. Very natural, because we don't want to use our wastewater when we have to pay more. But when the cost drops down, you have a luxury to use it as much as you can. So basically, the marginal benefit is what is very high in the early stages, and whereas the marginal benefits drop as the quantity increases further. So there is a supply cost as well associated with that, because when to supply that water, we got to use energy, we got to use the pumps, we got to use the resources. There is a supply cost that is also associated with that. So what is the optimal pricing point at which the water can be made available to the customer? Let's think about the seasonal variations that we are getting to see. Summer, we have a huge stress in the water. Probably on a rainy season, the stress might come down because of the availability of excess water. But then can we allow the people to basically use the variable tariff structure basically to control the water system better? How? Because if I have excess water, I'll start watering my garden. I will start washing my vehicle. I will start using water for all my applications. So whereas when the cost gets higher, then I will be a little careful in terms of managing that. So how the algorithms that I am using to basically predict the cost aspect better, and then how the better prediction can be embedded into deciding the right pricing point, is all the cost benefit analysis that we can use. The other use cases where I basically think we should be focusing on is non-revenue water minimization, which is a major topic which is studied extensively in India. We know that it's difficult to control. We are somewhere around 55% with non-revenue water. That means 55 to 60% of the water in our network gets lost without even getting accounted and not getting paid. So how to minimize that, we have to now move from intermittent to 24/7 as the first step. So only after that you will be having better control over the leakage points and arrest the leakage points more effectively. So that's the work which is well in progress, and there's a lot of smart solutions that are required to control the non-revenue water. Flash flooding, and due to the rains and due to certain events that cities are experiencing today, how do we basically minimize that? How do we have a better control over the drainage system and the visibility to the drainage system? How do we make them, how do we proactively, channelize the water better so that, all this flooding is avoided? Of course, pump operation is a major source of energy in the smart city framework. So a lot of energy is being spent to manage the pumping requirements. So how do we basically use the pump and efficiency curve to get us to the optimal point where this energy reduction can be achieved? Is one point there. Of course, the pipe burst management and the capex minimization is a huge topic, and it's a topic in its own right. So there are multiple factors which contribute to the burst in the pipeline. It's just not about the age of the pipeline, the where it is laid, what is the property of the soil, what is the kind of road that is being created on the surface, how many vehicles are moving, and what is the material of construction. So all these parameters, in fact, decide the state of the pipe that is underneath. So when we use all these parameters, you can accurately predict, and we have done that, and we, to the extent of 80 to 85%, we can say that whether the pipe is going to fail, or it's going to survive for one more year, or it's going to have multiple failures in the span of 1 or 2 years. So that is the level of details what we can extract. Now, what is the use? You can operate much better, because wherever you have a higher tendency to failure, you can basically move in assets there upfront and early you can be more proactive in your approach, you can be ready with the pipe that is due for replacement, and then you can manage the whole bursting operation very effectively. So that is another area where the smart solutions can be useful. Of course, watershed modeling and more computer vision, these are the techniques which Singapore has used extensively. We can probably take a leaf out of it and then use those things to bring in the smartness. So overall, we have to, as a conclusion, I would say that we got to honor the 4S, that is the safety and the sufficiency and all those aspects. We got to, in fact, honor that and then use them as the objective in terms of developing the smart solutions. And it goes with the collection of the right data and the right information to get the right outputs. And the water recycle is the key, and we cannot avoid it. I mean, that's something which we got to be mindful now, and we need to go with the recycling of the water as much as possible and still ensure that the quality is not compromised. With the smart water management, considering the recycle as the key challenge, how the quality, quantity, and the aspects can be continuously managed throughout the prediction horizon is what we got to be thinking about. So with that, I just wanted to stop this particular talk, and I would be happy to take questions from you. Yeah, thank you. So the question is that wastewater, management, there are sensors and automation that other countries are using, and why we can't, in fact.
I don't know if there are other countries are using. Okay. My question is, are they using? If so, why are they using? Because for them also it's not.
Well, let me say this, not actually, but then the technology that other countries, Western countries use in the wastewater may demand certain minimum, automation in the system. I will give a very simple example. What we use in India is mostly a technology called as the SBR in the wastewater, sequencing batch reactor. It's a batch operation which goes with just water coming in, spending some time in the system, and then going out. So that is in short, what SBR is about. The Western countries are basically using technologies, which are highly advanced. They call as a MBR, membrane bioreactor. So there is a membrane which basically separates out the bugs, and then there is a continuous recycling of the water within the system on a continuous basis, and you got to keep the membrane clean. So when this objective is totally different, so there is some level of automation that membrane bioreactor demands over the SBR. SBR also operates in a certain way, but the level of automation that goes into the MBR is far more advanced than SBR. So with whatever automation MBR has and SBR has, beyond that do we need to go is definitely a question, right? And when you want to achieve something beyond that, then the value creation and the value becomes a question mark. Are we going to proportionately create the additional value to the extent to which you will be spending money, or it's not proportional? That's the question that we got to answer, and it's true for both the technologies.
Thank you for the interesting talk, Dr. Prasad. I invite Professor Raghunathan Rangaswamy, Dean Global Engagement, to hand over a memento. The next talk of the session will be by Mr. Rohit Raphael. Rohit is a researcher with the Robert Bosch Center for Data Science and Artificial Intelligence. The title of his talk is Data-Driven Monitoring of IoT-Enabled Water Distribution Networks.
Yeah, hello everyone. Good day to all. My name is Rohit. I'm working with Professor Swarup in the Department of Chemical Engineering, and I'm working on a project funded by RBCDSAI. So the topic for my project is actually data-driven monitoring of IoT-enabled water distribution networks. So basically, I'll be talking more on the technical and instrumentation aspects of this project. So let me start. So the first question is, do we have enough water? So is there enough water for a sustainable future for all the generations? So the answer is clearly no. That's the truth. So Da Vinci said that water is the driving force of all nature. If the water is the driving force of all nature, what happens if there is severe scarcity of water happening in the world? All the living organisms will be affected, and moreover, humans will be affected the most. And to be honest, I was really surprised to see this statistics done by this World Wildlife Fund. I never thought that they will be doing such a survey. So they found out that 1.1 billion people lack access to clean water. And 2.7 billion people are having scarcity 1 month per every year. And this can actually go up to 2/3 of the whole population by 2025. So if this is the case, we definitely need to act now. Otherwise, it will be very bad in the future for all the living organisms. And I also like to recall the words of Dr. APJ Abdul Kalam. Future would be over water. So it won't be over money, it won't be over data, it won't be over information, nothing, but it will be water. So unless we are able to survive, nothing else matters. So what are the issues here? So the main issue with water is the uncertainty. So when we are utilizing a critical resource like water, there is large uncertainty involved in that one. This is mainly due to lack of quantitative monitoring. Most of the cases, water is just supplied. We don't know how much it is supplied. We don't know where it is supplied. We don't even know whether all of them are getting, there is equitable supply. We don't know anything. So unless there is a proper quantitative monitoring, there is no point in having a good data regarding the water resource. So we have to develop a system that actually measure the water that is being supplied to each and every node. By node, it can be a domestic house, it can be a factory, it can be an industry, it can be a community like IIT Madras. But unless we are actually having a properly monitored, quantitatively monitored resource for water distribution, there is no point in having this at all. So there is other issues like leakage and wastage. So I recall seeing some issues inside campus itself. Actually, this ball float valves in the overhead tanks of buildings, they were actually leaking. And it's it went on for 1 month or something, and nobody was actually reporting it. So there comes the next point, the human ignorance. So some people might be aware of such issues happening, they may not be reporting. I was seeing that thing, I didn't report, it is an ignorance for my part. So unless we are also in a philosophical perspective, we are also aware of the issues related to water distribution. If we are not considerate enough to understand the issues, it's just a small amount of water is getting leaked, what will be happening? We are ignorant about that thing. But on the whole perspective, that might be a large wastage that is being caused at different nodes. We don't even know how many nodes are being affected with the same issue. So if all of us are having the same mentality, then that will lead to large wastage. So the solution for this thing is actually monitoring of these water distribution networks. And we can actually monitor the data, and we can actually analyze the data and find out solution for each and every point that I mentioned. So next we come to the implementation part. So Internet of Things. Basically, Internet of Things is just exchange of data between things. Things can be any nodes, it can be objects. So once we have exchange of data between the things, using some existing wireless or wire transmission systems, it can be considered as Internet of Things. So by implementing this technology into water distribution, we can actually devise a system that can be the solution for all our issues. So basically, we need to consider the low power aspect. So this aspect, what we are talking about is most of the system, it has to be battery powered. We can't just give mains power to all the nodes and just expect everything to work fine. It's not possible. Some of the nodes will be overhead tanks, they might be remotely placed. We won't be able to give mains power at all. So it has to be powered from batteries. And for that, the system should be a low power system. And another thing is like practicality and reliability of the data. So we should be devising system that can actually run for some time at least. I'm not talking about like 20 or 30 years, but at least like if it's able to run for like 5 or 6 years, it will be worth it. So it should be like practical and reliable. Next thing is the transmission system. So basically, most of the cases we'll be seeing GSM-based system that is actually using a SIM, and some data service provider will be giving some plans, and we will be paying for them like monthly or annually. And this system will be used for transferring the data. But when we are considering an IoT-based system, it's always better to go for a free spectrum system that actually we don't have to pay for it. So there are these ISM bands, industrial, scientific, and medical bands that are actually free to use. We only have to buy the device, and we can use these technologies like LoRa, HC12, etc., which can actually transmit the data without the help of any external service provider. So in our case, actually we are using certain tools like ThinkSpeak IoT Analytics Platform. It's actually a tool that is provided by MathWorks. And we are using Arduino IDE, Python, Grafana, SQL, etc. for the other analysis part. So this is actually a basic architecture of a water distribution network. So as you can see, in most cases, actually this is roughly based on the water distribution network that is present in this particular building, ICSR building. So we have like a groundwater sump that is actually getting data from the main supply system. So those, the supply to the sump will be gravity driven, and from the sump, the water will be pumped to the overhead tank that is actually distributing to the different nodes, like different places inside the building. It will be supplied from the overhead tank. So what we have done here is actually we are monitoring the data from each node, and we are actually transferring it using a gateway into a cloud server. So there actually we can store and visualize the data, and this can be actually further used for any kind of data analysis. So this IoT part in WDN. So basically in any IoT system, not only in WDN, any IoT system, we basically has this kind of structure. So the sensors will be there. The sensors in WDN mostly will be like level sensors, flow sensors. Actually, we are also working on something called vibration sensing. It's actually, I'll come to that the next slide. And the next thing after sensors is the powering. So powering is more one, like I told you, like low power is like a necessity for IoT-based systems. So if the powering is not done properly, it will fail, definitely. So we have to consider the type of power required depending on the topology. Suppose we are actually fixing a sensor on top of an OHT tank, like overhead tank, that doesn't have any mains power. So the ideal way will be to go for a solar panel with a battery system. So battery backup for the night time, and the solar panel will be charging it in the daytime, and that can actually power the module in a sustainable way. Or if we are having the unit inside a building, actually we have mains power. Actually we can just give mains power directly using an SMPS adapter, and it will definitely work. So depending on the topology, we have to select the power system. Next is the telemetry part. So telemetry part actually consists of the remotely placed sensors that has to transfer the data to the gateway. So mostly we are actually working on free spectrum systems like LoRa and HC12 for transferring the data from the remote nodes to the gateway. So the gateway will be connected to network or the cloud server using Wi-Fi or LAN-based system that is already available everywhere. And the data storage, analytics, and visualization part will be taken care of by the ThinkSpeak IoT Analytics platform. So I'll just give a brief idea about the sensors that we are using. So for the level sensing, we are actually using ultrasonic-based water level sensors. And for vibration sensing, we are actually using a gyroscope-based system for identifying any vibration in the pipeline. The reason for that, I'll come in the next slide. And for flow measurement, we are actually using Hall effect type flow meters. And coming to the wireless transmission part, this HC12 module is like a very small, cute little module that actually that's readily available everywhere. The advantage of this module is being like, it actually uses ISM bandwidth, so we don't have to pay for any provider. So it has 100 channels, so there won't be any interference in any of the clusters nearby. And the range of this module is around 1 to 2 kilometers. So it's actually ideal for any kind of indoor or outdoor applications that is actually spanning over a small area. It has actually 8 levels of power transmission. So depending on the requirement, we can actually change the transmission power. Now I'll just have a comparison with the other systems that we have for transmission, like GSM and LoRa. So why actually we chose HC12 module for this particular system, I'll just explain it here. So HC12 mostly compared to GSM, both HC12 and LoRa has many advantages. The main thing being it doesn't need any service provider. But why I went with HC12 and not with LoRa is the reason I'm going to explain here. So the range of HC12 is actually much lesser than LoRa, but LoRa has an issue. It needs line of sight. So without line of sight, it will be very difficult for the data transmission to happen properly. But advantage of HC12 is that it, in smaller range, although the range of HC12 is much lower than LoRa, in that particular range, it will be more successful in transmitting the data because it has more penetration power over solid walls. So if you're using something like an indoor structure, like inside a building, if you want to monitor data and send it inside, or if the gateway is inside the building, if you want to send the data from the roof of a building and to a gateway that is inside the building, HC12 will be much more better than using LoRa. Although LoRa is great for like open, like completely open line of sight transmission, LoRa can work for at most like roughly 10 kilometers. But in real world usage, that actually never happens. Line of sight will be a big issue. So that is the reason why we actually went with HC12. Then other thing is about the lower power consumption. So I'm just combining the free spectrum versus GSM here. So GSM usually needs large power. So for transmission, it takes roughly around 2 amperes. Whenever it's transmitting, the current requirement will be roughly 1 to 2 amperes depending on the module. But when it comes to open spectrum things like HC12 or LoRa, it is always less than 100 milliamps while transmitting. And while it's not transmitting, it's like very low current consumption is done by these modules. So that is the main advantage of using HC12 and LoRa when it comes to IoT-based systems. Because IoT systems are all battery-powered. We cannot drive like an GSM-based module for battery-based system if the transmission is quite frequent. Suppose if it's done like once in a day or something, it's fine. But most of the cases, if you want to do proper data analytics, the frequency of the transmission should be much more frequent. Okay, so this is why this is the explanation of why HC12 is used in this one. So now it comes to the gateway part. So in this particular work, we actually use the Wi-Fi based gateway. The reason being it's basically using an ESP8266 module that actually uses Wi-Fi for communicating with the internet. So since we are using a cloud server for all the data analytics, data visualization, and data storage part, we need a gateway that can actually access internet. And using an ESP8266 make it much more cheaper. So one of the main perspective was economic feasibility in this case. So since we are using this module, it's much more easier and much more cheaper to implement this particular system. So we actually initially use a Raspberry Pi based system for gateways, but the issue was like Raspberry Pi is like, now the main issue is it's not available. Like the last 4 or 5 months, we were not able to get like a single module of Raspberry Pi. And it's very expensive compared to ESP module. It's almost like 20 times more expensive. So going for like a very cheap module that can actually connect to our cloud server was the only way. So we actually went with an ESP8266 based module that actually collects the data using an HC12 receiver that is connected to the ESP module, and it will actually push the data to the cloud server. So now coming to the data visualization analytics part. So what we are using is ThinkSpeak IoT analytics platform. So it's actually provided by MathWorks. So it has a free version, but it also has a like paid version that we are actually subscribed to. So the advantage of this thing is like it takes care of almost all the perspectives of data, like from storage to visualization to analytics. Anything can be done using ThinkSpeak. So since it's a cloud-based system, accessing the data from anywhere, it's quite easy. So we actually went with ThinkSpeak for the data analytics part. So this is the dashboard that we have in ThinkSpeak. So this particular dashboard is actually of this particular building, ICSR, the building that we are sitting right now. So I'll just show the real-time data that is being collected here. So this data is actually the live data. This is the live data that is being actually happening right now. So if you look at the first chart, it's actually the tank level. So this is the actual OHT that is on top of this building. So if you can see, it was actually in tank level, this is actually higher means less water. So this is the distance from the surface of water to the top of the tank that is actually being measured. So if you can see, up to around 8 o'clock, it was actually low. The level of water was low. Then the pumping started and the level actually increased. And we were all here and we were all using the washrooms, etc. here. And the water level is actually reducing again. So by 10 o'clock, 10:30 after the break time, the water level is being reduced. Next part is the gyroscope part. So another main thing that we are doing here is like in order to measure flow. So in most WDNs, the main issue or main challenge that is being faced is like measuring of the flow. Flow meters mostly, whether it be electromagnetic or ultrasonic, all of them are like very intrusive. If you want to install a flow meter or if you want to maintain a flow meter, it's very difficult. We have to cut the pipeline, we have to connect flanges, we have to thread it, we have to fix these things. So this is one of the most most difficult part in any kind of WDN monitoring system. So we ourselves actually, when we were doing in the initial stages of this project, we were actually connecting some flow meters, and it was like hectic to get it done. We need to get the help of plumbers, and they have to come, they won't come at time. We were not able to fix it properly. So all these things were coming. So then we actually thought about measuring the flow using a non-intrusive method, like a proxy parameter. So that is where vibration actually comes in. So what we basically did is like use a very cheap MPU module, MPU 6050. It's actually the same kind of module that's being used for drones. Stabilizing of drones is done by the same module. So the same module, when we are actually considering the gyroscope part of that module, we can actually measure the vibration that is happening in a pipeline. So in the second field 2 chart, if you can see, this actually gives the vibration data, the gyroscope data from the pipeline. So when there is no flow, the gyroscope data clearly shows a deviation. When the pumping is starting, so every day the pumping is starting at around 7 o'clock. So at 7 o'clock, the vibration increases drastically, and we can actually see that flow is happening. And most cases, since the pump is having a uniform pumping rate, we can actually find out the flow rate or the actual quantity of water that is actually being pumped to the overhead tank just by looking at the vibration data. So using this gyroscope value or vibration data, the main advantage is that it's completely non-intrusive. It just had to be fixed outside the pipeline. We don't have to actually disturb the line at all. And the other advantage is if you are actually looking into the data more, we can actually find out different levels of flow happening in this one. So in field 5, actually I like to point out a few points in field 5. The field 5 is actually corresponds to the sump level of this building. So this groundwater sump actually has a level sensor fixed on this thing. And if you look into this part, so this actually looks like a noise part. In most cases, people will be considering this noise, and we will actually remove it, saying that it's an outlier. We don't need the data. But what is actually happening in this part is the filling is happening. The filling of the sump is happening. So this is gravity-driven filling is actually highly turbulent, and because of the turbulence, ripples will be caused on the surface of the water. And the ultrasonic sensor is actually picking up that ripples, and it is actually showing as a noise. So what will otherwise be considered as a noise is actually useful here to identifying the filling time of the sump. And after that one, we can see at around 11 o'clock, it's actually stabilizing. So I'll come back to the presentation now. 2 minutes. So these are some of the results. So in the interest of time, I'm actually not explaining the part on the results. So here what we are actually done is we have estimated the flow just by looking into the status of the pumps and the level data without actually measuring the flow. So we actually found out that the accuracy is around accuracy is always above 97%. So these are all the results that I have. So for concluding, I just want to say that it's very crucial and very important to have a proper monitoring system for any water distribution networks. So we actually use an IoT-based system with HC12 that was actually we were quite successful in getting the data, and the data can be actually used for further analysis. And the future work is actually the scaling of the present system to a larger geographical area so that we can actually collect more data. More data means more knowledge. So I think it will be quite crucial for any kind of analysis and research continues. So I just want to acknowledge all this, everyone, especially RBCDSAI for funding this project. Thank you.
I'm sorry, but we'll skip the Q&A for now. You can catch them during the break. So thank you for the talk, Rohit. I invite Professor Balaraman Ravindran to present Rohit with the memento. With that talk, we come to the end of the session on smart water. We will now move to the final theme of the day, smart grid. Kicking this off, we have Professor Shanti Swarup delivering the keynote address. Professor Shanti Swarup is a professor with the Department of Electrical Engineering, IIT Madras. Prior to joining the Department of Electrical Engineering, he held positions at the Mitsubishi Electric Corporation, Osaka, Japan, and Kitami Institute of Technology, Hokkaido, Japan, as visiting research scientist and visiting professor respectively. His areas of research are computer modeling, energy management systems, automation, numerical protection, and digital relaying of electric power systems and smart grids. I invite Professor Swarup to the stage to deliver the keynote address titled AI/ML Applications to Smart Grid.
I'll try to make the talk more interesting. Okay. Thank you for inviting me here. Smart grid is a new area, so I want to introduce the topic so that everyone appreciates. This is the contents of the presentation. I divide into 4 parts. What are smart grids? The role of smart grids in smart cities, and how artificial intelligence plays a role in smart grids. In power system, we call it as computational intelligence, okay, which is a part of AI. And what are the application area of AI and machine learning in smart power grids? And finally, some of the research work carried out by our research scholars. We call it as a Smart Grid Research Computational Lab at IIT Madras. This is a brief introduction about my research. We have a power system engineering division. Our students have started a Smart Grid Computational Research Lab done by our students, so I want to highlight that. Let us see what are smart power grids. Just to say smart grids, it's a new term. Many people have different definitions of smart grids. Okay, let us see what is the evolution of smart grid. Before smart grid, we had only theory and simulation. We used to do mostly theoretical studies. To obtain data, we need to do simulation. We make a lot of assumptions and approximations to simplify the computational analysis. It's from theory to simulation. During smart grid, we had large amounts of data, only data and information. This is called as data explosion, resulting in large amounts of data called as big data. In this data, we have information, from information to knowledge, and knowledge to decision making. And we have data science, which is coming into picture. You might have heard about IIT Madras offering a course on data science. This is not the same as data engineering, as you might think. Smart grid. Now let us see what is called as smart grid. Smart grid is what is called as informed decision making. It's mostly decision making, but it informs you before making a decision. So it comes under the management as well as power engineering as well as computational intelligence. What is the future of smart grid? It's mostly theory, information, and knowledge. We have 5G, smart grid communications, virtual engineering, visualization, okay, information theory. Of course, AI, deep learning, machine learning play an important role. All of them aim to have what is called as an autonomous systems. If you want to put all of them into picture, smart grids and AI/ML, it's mostly intelligent data and knowledge. Let us see how data, information, knowledge are different. As it is shown here, data contains information and knowledge. Information as meaningful and useful data. Knowledge, assimilation and linking of high quality data for decision making. Intelligence is mapping of data, information and knowledge to decision making. And intuitive learning is where AI, ML and deep learning come into picture. This is where complex systems for autonomous system. This is where a smart grid is nothing but an autonomous grid. With this is the typical architecture of a smart grid. As you can see here, we have renewable energy, green energy, we have fossil fuel plants. These are the consumers, electric vehicles, and these are smart homes and factories. This is a typical smart city and the smart grid. A smart grid is a network of energy resources and loads interconnected by means of power, communication, and information paths. This is called the digital transformation. Smart grid is called as a digital energy. Many industries have transformed their names from conventional energy to digital energy. These are the various technologies used. You have data mining here. AI plays a very important role. And you also have blockchain coming into picture. And several use cases. So smart grid, industry plays a very important role and finds smart grid more fascinating because they want to see how to use smart grid technology for the future applications. Now, the speaker about water distribution network, this is similar to that. A power distribution network is similar to a water distribution network. IoT plays a very important role here. If you see here, this is the power generation. Okay. Thermal, hydro, you have renewable, solar. These are the various power generation. And these are the consumptions. This is the transmission, this is the power. Generation, transmission, distribution. This is called the consumer, consumption. Here IoT plays a very important role. Here you have energy storage, you have a power market and virtual power plants. Okay? This power market and virtual power plants are the future of smart grids. That's why they're introduced here. IoT and IIoT plays a very important role in smart grids. Let us see how. And smart metering is the basis for smart grids. Where smart meters, where residential smart meters, they use home area network, they send information over the communication lines, where all the measurements are collected. This is called the aggregation. All the data is collected and transformed over to utilities. This is what is called the smart grid or advanced metering infrastructure. The smart grid widely uses and depends on smart metering. Without smart metering, there is no smart grid. This is the roadmap for smart grid applications. Okay? This is the smart power grid, which forms the base. Next, you have the smart electricity service, where you have the pricing schemes, real-time billing, etc. Then you have the smart consumer, smart renewables, and smart transportation. So we start with smart consumers, and finally, for a national-wide smart grid at 2030. This is what the Prime Minister's roadmap to have all renewables by 2030. Let us see what is smart grid. We call it as a layered architecture. Earlier, a power grid is only a physical layer. This is called the power system, this is a physical layer. Along this power system, several digital layers have been created. This is what is called the smart grid applications. Starting with component layer is the physical layer, and communication layer, information layer, function layer, and business layer all comes under smart grid applications. Because of this, IT companies try to take advantage of smart grid and try to come up with good products, challenging products here. This is what is called interoperability of smart grid. Okay? The physical layer is only one. The digital layer consists of smart grid applications. You can even think of a decision-making layer at the top. You can see the mapping from generation throughout the business layer, the transmission, and the customer service. This is what is called the smart grid architecture. The architecture used by all utilities. ABB, GE, all of them follow the same architecture, but different layers and different functions in each layer. This is another description of a smart grid. You can see a grid. Okay? You have generation, you have transmission, and you have distribution. Usually this is called as a power consumer. Earlier we used to call it as a load. It acted as a passive role. Now these consumers are very active. They're called as prosumers. You can see here most of the activity takes place in the consumer side, where you have renewable energy, energy storage, EV charging. Most of the smart grid takes place in the power consumers, as shown here. If you see here, this is a typical diagram of a smart grid. It's called a smart grid energy management. You have generation, transmission, distribution, and the customer. Smart grid has introduced many new technologies like dynamic pricing, energy management, bidirectional metering, distributed storage, electric vehicle, smart appliances, everything. If smart grid were not there, only we would be limited to generation, transmission, distribution. This is what the bidirectional flow of power and information. And it has introduced many devices, many business applications. Smart grid has introduced many business applications and technologies like demand response, etc. Now, how does AI come into picture? Let us see AI in energy industry. Let me start with energy industry, then I'll go to smart grids. If you see here, AI plays a very important role in power grid, where smart grid is one such thing. Next, AI in power consumption, mostly smart home and smart meters. Next, AI in the virtual power plant. Remember, I showed you virtual power plant in IoT. Okay? Here they do what is called decentralized plants. And AI in electricity trading. Electricity markets, where electricity used as a service, and not as a service but as a commodity. You buy and sell energy. If you observe here, there is a forecast which is both here as well as here. So forecasting plays a very important role. AI plays a very important role in forecasting. Forecasting of the load, forecasting of the price, forecasting of the energy consumption, etc. Now, if you see, how is AI different from computational intelligence? Remember, I was talking AI as computational intelligence. Okay? Smart grid has many applications, either AI and computational intelligence. In AI, we have many things like qualitative reasoning, qualitative simulation, etc., even multi-agents. In computational intelligence, okay, neural networks, fuzzy, and etc. When it comes to the applications, okay, data filtering, processing, and diagnosis plays a very important role. Here, energy management system. And of course, optimization. Smart grid optimization is an area which is gaining more importance nowadays. Now, let's talk about machine learning. Okay? If you see here, machine learning in power systems, mostly for predictive analytics. We had a talk today from L&T. What is the role of analytics? So, machine learning pros, mostly predictive analytics, as I said, mostly forecasting. Load forecasting, generation forecasting, energy consumption forecasting. Forecasting plays a very important role. And if you see here, decision making, mostly for the control center, and asset management. This is the most important thing. Asset transformers are our assets. Okay? The life of a transformer is very, very important. If you can predict how and when it's going to fail, okay, we can have what is called as predictive maintenance. That's called as predictive analytics. Predictive maintenance, prescriptive maintenance, all this comes under machine learning. How do you apply AI and machine learning to smart grids? This slide describes, okay, the various areas of AI, mostly AI, machine learning, deep learning, mostly based on the data it collects. This is what is called as the smart meter data. And where they are used, as I said, energy trading, energy storage, okay, energy hub, dynamic tariff is nothing but the dynamic pricing, smart homes, etc. This is where AI and machine learning are used for smart grids. This is what is called peer-to-peer energy trading. It is called electricity markets, where energy is used as a commodity than as a service. Some of the smart grid applications are automated demand response, load aggregation, and blockchain. Blockchain applications are cryptocurrency. They are gaining more importance. Okay, even though I'm not going to discuss here, the different types of customers, how they use AI applications for demand response, load aggregation, and they use, okay, blockchain applications for different energy billing. I got this from the net. I want to share with you, okay, various AI applications. If you see here, this is the domain: generation, distribution, and smart consumption. And these are the applications, and these are the AI techniques. You can see here, many AI techniques are used in the present context. I've separated them here for easier viewing. You see here AI techniques, mostly they use multi-agent, they use okay, ANN methods, they use, okay, various deep learning methods. Each method for different type of domain. For distributed generation, they use some AI techniques. For distribution management, some AI techniques. And smart consumption for AI techniques. You can't use the same AI techniques for each and every domain. Okay, different domains require different techniques. Who are the users? These are distributed energy resources. They have the transmission and distribution. You see here, there's a forecasting, and there's an electricity market. The forecasting is very, very important. Machine learning and AI are used for forecasting of the energy and price. And this is a customer network. If you see here, the customer network has EV charging, energy storage, even a forecaster here, smart home, etc. What are the new research areas? I got it from the net, okay? Application of machine learning and deep learning for smart grids. These are the research areas students would like to work on, so I want to share with you. Electricity demand prediction, electricity theft detection, load balancing, stability, security in smart grids, data management and grid analytics, intelligent monitoring systems, integration of soft computing and meta-heuristics. These are the widely used applications. Okay? This slide is self-explanatory. Machine learning in smart grids. These are the machine learning applications and machine learning challenges. The most widely used application is fault classification and location, followed by load management and security assessment and pricing. Why do you need machine learning for this? Why can't AI? See, here AI is different from and machine learning is different. You have to learn from the past historical data, from the trend, from the data you have to learn what is the pricing. And this is machine learning challenges. Now, I'll start with game theory. Some of our students used game theory in power systems and smart grid. What is game theory? How is it related to AI and machine learning? Okay. This is a typical game theory in power systems. Mostly this is a typical Indian energy market. You have various private markets, electricity markets, retail markets, wholesale markets. Okay. Usually the Indian market is privatized. We have many private generators who want to supply power. They have different prices. They want to compete in the market. Okay. The privatization of electrical power market has introduced competition and choice of electricity. Okay. The players are competitors. Why? For the market share and would like to capture the market for supplying the power. Okay. This has led to the game theory. The more the players, the more is the competition. Okay. Many private players they want to participate in supplying power to the grid. This is what it is. This is a typical diagram. This is the D is the present day, previous day, and D minus N. This is how a forecasting is done. This is D, present day is called the balancing market, real-time market. The offers are nothing but the bids. Okay? D plus 1 is the forecasting for D plus N and D minus N. Okay? Game theory is a combination of AI and machine learning. This is how me and my students think of game theory. Why? AI is nothing but intelligently identify the bidding strategies. These bidding strategies are offers. Machine learning is to learn the bids to be placed from the past. Based on how he has been bidding in the past, you try to learn. Okay? Predict the bid prices and volumes. AI is different from machine learning when we look at it pricing. And how about game theory? Game theory ensures that a fairness. It's like a policeman. He ensures that there is a fairness in allocating the bids to the different players. This is how we introduce game theory as a combination of AI and machine learning. This is a typical example, how they are used. This is the power grid and this is the demand side. What you see here, different users. These users are the consumers. They can also be players. This is the price and this is the demand. But when it comes to a smart grid, this is bidirectional. Same diagram shown here, demand side, demand and price. The smart grid introduces a large number of interesting problems and optimizations to solve. Okay? The game theory encourages end customers to consume consume green energy. Green energy is nothing but renewable energy. Here the players are the operator and the consumer. This is the operator and this is the consumer. And introducing a dynamic pricing strategy. The price is not fixed but variable. So objective of the players is to reduce the energy cost and to have some fairness in the green energy distribution. This is how the problem is formulated. Next, I want to show some of the research we are doing at IIT Madras, some of the work done by our students. Our students have set up a smart grid computational research lab. We have collaborated with different universities. Okay, we have a LinkedIn link here. We work in different areas, and also we work with different industries have shown interest. And recently, we started with a grid automation and digital twins with a company called Accenture. They've shown more interest, okay, and they're driving us to realize their objectives. And we have one power flow control. It is a transformer asset management. These are live projects which we are doing. It's not just teaching. We are practicing what we preach. And one of our students' work had come in a journal recently. He was using a cyber security attack, which one of my students is going to present after this. How they use a machine learning technique for classification is a typical example. And some students try to use machine learning for inertia monitoring. You know, in machines, you have large turbines. Detection of mechanical power changes using Q learning. This is one of the present, they use a Q learning algorithm to estimate the inertia of a machine. This is the mathematics behind. This is called the swing equation. This mechanical power is supposed to be constant. Okay? This electrical power and frequency keeps on changing. We try to estimate the PM. If there's a change in PM, then they say that inertia estimation is valid. So we try to use Q learning for estimate the inertia of a group of generators. And another student is working on phase shifting transformers using machine learning. These are some of the areas, hidden tap change detection. Okay? This is nothing but a classification problem. He used and false machine learning based classification algorithm. This is the current research going on. And some of the research we have, one of our students has done on a game theory for EV charging. This appears more like a hypothetical thing, but this is gaining more importance. Why? Because this is how it is. We did it for a 132 kV Nagpur ring main distribution system. The aim is to identify which is the charging points, okay, for electric vehicles. In fact, this Ola station in Nagpur is very widely used. They use EV charging. We got the data from there. This is a typical ring main distribution system of Nagpur, and we try to simulate this, try to calculate the distance. Each circle shows the radius by which an EV can be charged. You can go to the next network and get it charged. You see here, here generation is there, the price is cheaper. Far away node, the price is expensive. Where to charge the electric vehicle? This is one of the applications where game theory and machine learning has been used. And another thing is what is called dynamic optimization. See, EV charging is an area which has gained more importance. This is a different EV charging. Okay, should we charge from which charging point? Okay, how much time should we wait? All these are research problems in EV charging where AI and machine learning are used. Okay, and this presentation will be made by Amulya after this. And I want to introduce what is called a virtual power plant. Okay, it's an autonomous microgrid. Okay, this aggregates the capacity of many diverse distributed energy resources, and is used in what is called a smart grid. This is how a typical virtual power plant looks like. What do you understand from this? Okay. There are different generation sources. Okay. Photovoltaic generation, energy storage, dispatchable loads, reciprocating engines, conventional engines, wind producer, many users and generation. This is the grid. A virtual power plant is an imaginary power plant. It's something like a power pool. Okay? It collects all the information from various resources and allocates the power to various load charging points. PCC is called the point of common coupling. This virtual power plant is the power plants of the future. Okay? They are gaining more because they use smart grid technology, information and communication technology. How they are being used in smart grid is still a challenge. We don't have such a power plant in our country, but in the next 5 years or less, we will not be surprised if we have one such in the near future. Yeah, this is how a virtual power plant participates in energy markets. Okay, energy market, the various home energy management system, okay, transmission system operator, distribution system operator, how they collect how the smart meters collect information and help in selling the energy in the grid. This is what is called energy trading or transactive energy. What is the industry relevance? Industry works on applied artificial intelligence, not on theoretical AI. Okay? Applied artificial intelligence, there are many domains, robotics, AI and ML technologies, and finally IT infrastructure. One such application we have doing on is a digital twin for a transformer. This is a typical transformer. It uses many sensors. Okay? Usually it's a black box. We only use some sensors on the outside to see what is happening. Is it possible to see what is happening inside? We use sensors, monitor sensors and collect the data and see what is happening wrong instead of what is happening right, when it is likely to fail. If you can predict a fault from occurring, you can separate the transformer, give it maintenance and connect it to the grid. This is what is called ETOS, Open Operating System for Transformers. This is what we are doing. This is what is called a digital twin for a transformer. If you go in detail, okay, this is a transformer, this is a equivalent circuit, this is called the physics-based model. Okay, this is what is called the digital twin of a transformer, which is widely used in smart grids to predict and also to maximize the life of an asset. In the Indian context, okay, this is the Indian Power Exchange. Okay, this is called India Energy Exchange. This is the Indian power grid, and the different states, we have different regions. Every 15 minutes, you will have a change in power. You try to monitor what's happening. Okay, we have what is called as market clearing price, and different blocks. If you see here, this is what is called the aggregate demand supply curve. This is what is called the supply curve, this is the demand curve, and this is called the market clearing price. This is done every 15 minutes. This is a real-time market, okay, and this is how the electricity price keeps varying in rupees per kilowatt hour, per megawatt hour. For 24 hours, all different states, this is how the electricity price keeps changing. This is the peak one, this is the peak two. How the peak price keeps on changing. According to this, the energy is traded, is bought and sold. This is where the relevance of smart grid forecasting plays a very important role. Whatever theory I have explained is more widely used here. And I'll conclude. AI and ML, not MIL, sorry, ML are widely used in power systems. Forecasting and prediction are the most important tasks in AI. And smart meter data is important for most of the AI applications. When you talk about forecasting, it is load forecasting, price and energy forecasting. All three are equally important. Okay? Prediction and trending behavior of residential household energy consumption using smart meter data is the challenge being faced now. Suppose I have smart meters at residences. What is the energy consumption of the consumer? Predicting the behavior based on past data is still a challenge. Okay? And predictive analytics is the outcome of smart grids. Okay? And game theory is an outcome of AI and ML. And there are several potential applications in AI and ML, mostly in the cyber security. And finally, the goal of smart grid is to have an autonomous, self-healing and a resilient power networks. This is the main aim of smart grid. What is the deliverable? We want an autonomous network which is self-healing, resilient, and informed decision making so that the power is available to the consumers round the clock 24/7. With this, I'll stop. I've taken more time. Any questions, feel free to ask. I think everyone is hungry.
So this is Dr. Aiml from IIP Visakhapatnam. So it seems when you don't have the power generation through the renewables, there is no idea of smart grid networks. Is it so?
Need not be. Okay. Smart grid with renewable is called as carbon footprint minimization. Okay. The main aim for renewable energy is to see that the fossil power generation is minimized. Many people call this as a smart grid. Integration of renewables is also called as smart grid. But the main aim of smart grid is using information and communication technologies to see how best you can use the renewable energy, when to use, how much to use. Okay, this is what is smart grid from a renewable energy perspective.
Okay, so it means that we can have still smart grids with the just power plant or hydro energy consumptions, and if you have the renewable energy sources coming into that, the complexity might bit increase because they are.
Yeah, it's not only increasing; it helps. You have more renewable energy at your disposal, so you can use more renewable energy and less of fossil fuel generation. That is also a part of smart grid.
Thank you, sir.
Okay.
Thank you for the talk, Professor Swarup. I invite Professor Ramakrishna Pasumarthy onto the stage to hand over a memento to Professor Swarup. So we have a few announcements. So we've been playing catch up with the schedule ever since we began, and we haven't done a good job. So we're going to change the schedule to be on time for lunch. We will break for lunch now and push the next scheduled talk to the post-lunch session. Lunch will be available in both the main dining hall and the mini dining hall. To manage time and space, we have arranged lunch for all registered participants in the main dining hall. This is the dining hall that we had refreshments in. And for the consortium members, speakers, panelists, and faculty, we have organized lunch in the mini dining hall. Whoever does not have lunch coupons can collect them at the registration desk, and we'll be starting again in 45 minutes. So please be sure to come back to the auditorium by then. Thanks.